Welcome friends. In this video we will discuss the difference between power density spectrum and energy density spectrum. Energy density spectrum is to be determined for deterministic signals from a finite sequence of data. That is, we know the signal and we will convert the signal into samples, or we can directly use the signal as an analog signal. So if it is analog signal, then we use XAT. If it is a sampled version of this analog signal, then we use XN. Okay, so because it has finite sequence of data, so it has finite signal energy, so it Fourier transform does exist, so it is easy. That is the energy, finite energy, it is less than infinite. So as per Parseval theorem, E is equal to XAT. This energy in time domain is equal to energy in frequency domain. Okay, so what is the method now? We will have this signal XAT. We will do the Fourier transform of this signal using the Fourier transform technique, and then squaring the Fourier transform, and we will get the energy density spectrum, because energy is proportional to this term. So this is the methodology. Second method, we can also use that we know the autocorrelation also. Autocorrelation of that XAT deterministic signal is XAT plus tau, and by this formula, and then we find that, or obviously Wiener-Keynesian find that autocorrelation and power spectrum density are Fourier transform pair. It means if we do the Fourier transform of this signal, then we will get the power spectrum energy density spectrum. So we can have two methods. First, we can find the autocorrelation, and then we can have energy density spectrum, or we can directly have the doing the Fourier transform of this and signal and squaring it. In discrete, if it is XN, suppose it is sampled version, then we have this two representation, that is power spectrum density. Remember, we used capital F for analog, we use small f for discrete frequencies. Okay, we use T for time, we use K for discrete version, and N is for discrete time. So this is the power spectrum density using autocorrelation, because autocorrelation Fourier transform of autocorrelation is power spectrum density, and it is same in discrete domain. And what is autocorrelation? Autocorrelation is X star n, that is Xn plus in discrete case, that is summation. This integration is represented by summation, changed by summation. But in power density spectrum, it is to be calculated for stationary random process which has infinite energy, finite average power. So infinite energy, so Fourier transform does not exist. Fourier transform does not exist. This condition holds not true. So what we do? We do autocorrelation function of this stationary random process. We find the autocorrelation function, and look at the difference. Here we use autocorrelation with R when it is deterministic signal, where here he uses autocorrelation using gamma when it is a random process. Okay, to differentiate the things. And then we do the Fourier transform of autocorrelation function similar to that one, similar to this case, because this case does not exist here. So we do Fourier transform of autocorrelation function, and this Fourier transform is now known as power density spectrum, because in this case we can see that autocorrelation function itself is squaring of this signal x into x. That is why we don't need to do square, okay, after finding the Fourier transform. So it is easier that doing the autocorrelation, finding its Fourier transform, it is power density spectrum. Okay, so this is the energy density spectrum estimation technique, mathematical technique, you can say. That first, analog signal is sampled to make it discrete signal xn. It should be deterministic finite duration sequence. We have two methods now, direct method, indirect method. We have discussed in the previous slide. Direct method is compute Fourier transform of xn, that is cutting the xf and squaring it, and we have the energy density spectrum. In indirect method, we can have the autocorrelation method. Compute autocorrelation first from the sequence, and then finding the full transform of this autocorrelation function. Okay, and we have the energy density spectrum. So these are two methods, and we have implemented a MATLAB code for this finding the spectrum of a cos signal. You can check it and find the output, how it looks. Now some properties of power density spectrum. We know that a stationary random process is an infinite energy signal, hence its Fourier transform does not exist. So what Wiener-Khinchin theorem says that to obtain spectral characteristics of random process, Fourier transform of autocorrelation can be used. So distribution of power with frequency is given by for stationary random process using autocorrelation function. And we have that autocorrelation function time and frequency, a Fourier transform pair. It is Fourier transform, it is inverse Fourier transform. Okay, it is in time, it is in frequency. So when time equal to 0, then tau equal to 0 may, then this equation becomes this one, because now it is 0 here, exponent is 0. And we know that from the property of autocorrelation, gamma x x 0 is equal to E x squared t, we have done in previous video, previous part. And concluding both these cases, what we find that it from this case we find that it represents average, E for average, mean or average power of signal of signal or random process. X is random process here, so it represents average power of random process, and this represent area under the function gamma x x f, area under the function. So both are same, represent average power of the random process, which is nothing but the area under the gamma axis f. So it means gamma axis f can be represented as similarly as power density spectrum. That's what Wiener-Khinchin proved. If random process is real, then gamma axis tau is real and even, gamma axis f is real and even. You can always understand with the argument. If f is given, that is Fourier transform, its gamma is capital. When tau is given in argument, then gamma is small. Okay, it is in time domain. And both are statistical autocorrelation. We call it statistical autocorrelation. If random process is complex valued, gamma xx tau is equal to gamma xx minus, because it is even function, it has the property. And by this property, we can prove that, but we will not prove here. We can prove that gamma xx f is always real function. Okay. So for now, this is the difference between power density spectrum and energy density spectrum. In the next part, we will do periodogram method, and please watch the next video for periodogram method. Thank you very much.